Okay, so welcome all to today's session, which is the last of those dedicated to particle identification. So we will begin with a 25 minutes presentation on PID at PHENIX by Roli Esha, which will be followed by a question and discussion session with our panel today that consists of Roli, Chitrasen, Y, and Yanxi Zhang. And this discussion session will be moderated by Subhasish Chattopadhyay. So first, we will have the presentation on PID at PHENIX. So you may please ask the questions in the chat box, which we are keeping track of, and then maybe in the end of the talk, we can narrate the questions to Roli, unless it's a very urgent question, in which case you can just go ahead and ask. Okay. So over to you, Roli.
Okay, thank you. Hello, and thank you for the opportunity to talk about the PHENIX experiment. I will start with a historical preview, then discuss the detector setup and some of the major results. So, there is a little bit of a problem. I may need to share again. I'm not able to change slides. Okay. Is this fine now?
I think we still don't see your screen.
Oh, okay.
Yeah, it's fine now.
Fine?
Yeah.
Is this okay? Yeah.
Yeah, this is fine. Yeah.
All right. So, back in 1991, when RHIC asked for detector proposals, similar to what EIC did last year, STAR was selected to be the more generic detector. 3 proposals, one focused on electrons and photons, second on muons, and third on high PT hadrons, were asked to merge together to form the second detector. The charge, as it read, was to design and build a specialized detector to measure rare processes involving photons and leptons. From the ashes thus rose the PHENIX experiment, and hence the name, a pioneering high-energy nuclear interaction experiment. 4 major detector systems were set up around the 4 interaction points around the RHIC ring: Phobos, which concluded in 2005, Brahms, which concluded in 2006, PHENIX at the 8 o'clock position, which concluded in 2016 after a successful 16 years run, and STAR, which is the only running experiment at RHIC today. Through its 16 years of operation, PHENIX recorded and analyzed data from 8 collision systems and 9 collision energies. The figure on the left is the wide view of the detector. On the top right is the side view with one of the arms. On the bottom right is the event display. When it was commissioned due to shortage of funding, PHENIX was designed as a 2-arm spectrometer. But before delving into the detector components, particle identification 101. In order to uniquely determine the form momentum of a particle, we need to accurately and precisely measure any 2 of the following: energy, 3 momentum, or the velocity of the particle. Energy can be measured by techniques of calorimetry, momentum by tracking the particle in the magnetic field, and velocity by either measuring the time of flight, that is the time taken to cover a distance, or using the Cherenkov phenomena, where the particle traverses the medium faster than speed of light and leaves behind a cone of light, the solid angle for which is given by the refractive index and the speed of the particle. With the 4 momentum established, the particle is uniquely identified. Sometimes, to gain accuracy or precision, we may use all 3 of these techniques. PHENIX, like most large-scale experiment, is designed as an onion, where every layer serves a very important purpose. It starts with the determination of the collision vertex in the innermost layer, to momentum measurement or tracking the particle through the magnetic field, to identifying the particle, and finally the measurement of the energy of the particle. PHENIX is subdivided into 2 main subsystems, the central arm and the forward detectors. The central arm consists of detectors which are employed to measure the properties of the produced particles in the mid-rapidity region, which is in the plane transverse to the beam direction. The forward detectors measure particle properties in regions where pseudorapidity is greater than 1. The plot on the right shows the configuration of the PHENIX detector subsystem during its last run in the year 2016. The top panel is the central arm, while the bottom panel is the forward arm. On the left is a phase space plot with pseudorapidity on the x-axis and azimuthal angle on the y-axis. The differentiated regions correspond to acceptance for different particles. The magnets are at the core of any large-scale experiment. The magnet subsystem in PHENIX can be divided into 3 sections: the central magnet, the ones in the north arm, and the one in the south arm. PHENIX employs a 0.9 Tesla Helmholtz coil in the central arm that can be operated in 3 different configurations: plus plus, plus minus, and the outer coils only. In the plus plus configuration, the field from the inner and the outer coils add up, while in the plus minus configuration, the fields can be tuned to selectively cancel in a region around the beam direction. When dealing with the magnetic field, a good rule of thumb is that a 1 Tesla field would bend a 1 GeV particle by 1 millirad or 17 degrees. Now, let's start peeling the onion layer by layer. Global detectors are used to characterize the event, from trigger to the interaction point along the z direction to determination of the collision centrality and the reaction plane. The most important detector used in PHENIX for this particular purpose is the BBC, the beam counters, located in the north and the south arms. In the earlier runs, ZDC or the 0-degree calorimeter was also used in conjunction with the BBC to determine the collision centrality, but more recently only BBC is being used. For a more precise reaction plane determination, forward silicon detectors can also be used. The BBCs are quartz Cherenkov radiators with meshed dianode photomultiplier tubes. There are 64 elements in the north and south arms each. From the signal arrival time, which is like Tn and Ts, the N for the north arm and S for the south arm, the Z vertex of the collision can be determined with a resolution of 6 millimeters. The T0 for the collision is determined with the resolution of around 20 picoseconds. The photo on the right shows the dimension of each BBC element. Next, we move to tracking. The main detectors used here are the drift chambers and the pad chambers in the east and the west arm in the central arm. In PHENIX, the tracker lies outside the magnetic field, which implies that the track segments measured are actually straight lines. The drift chambers, which are the primary tracking devices, consists of 6 layers of nets. Due to the way it is designed, the X1 and the X2 layers are straight meshes that provide 6 hits in the X and Y component. And then we have the U and the V layers, which are staggered in a way that they would provide the Z component. Hoff transforms are implemented in order to identify the track segments. The drift chambers measure phi, which is the azimuthal location of the track at the nominal radius of 220 centimeters, and the inclination angle alpha, which is related to the momentum of the track. Pad chambers, which are at the back plane of the drift chamber, also provide the Z location for the track hit, but with a much higher precision. Tracking in PHENIX can be done with spatial resolution better than 150 microns in the R phi direction and 2 millimeters in the Z direction. 2-track separation is better than 1.5 millimeters. The relative momentum resolution of the PHENIX tracking is 1% quadratically added with 1% times p. This is the result of both the multiple scattering, which is the constant term, and the inherent detector resolution, which is the term that scales as p, as the momentum. The drift chambers extend 90 degrees in phi for both east and the west arms, with a pseudorapidity coverage of 0.35 around mid-rapidity. The arms are tilted up by 11 degrees in order to improve the acceptance for dielectron pair measurements, which, if you remember, was one of the key measurements in the charge. The figure on the left gives the dimension of the drift chamber. On the right, the pad chambers are shown mounted on the drift chamber. Hadron PID in PHENIX is mainly done through the time of flight detectors in the east and the west arms. These detectors provide the arrival time of the particle with the path length obtained from tracking. The velocity can be measured, and hence the mass of the particle is obtained using the given formula. The figure on the left is a section of TOF in the west arm. The plot on the right shows the charge divided by momentum as a function of time of flight for different tracks in gold-gold collisions at 200 GeV. With the resolution of 100 picoseconds at 5 meters, pions and kaons can be separated up to a momentum of around 2.4 GeV. Discussing the physics implications is another set of discussions itself. But to highlight some of the state-of-the-art measurements, the plot on the left is the V2 and V3 of charged tracks in the most central 0 to 5% small system collisions with P gold in red, D gold in blue, and helium gold in black as a function of transverse momentum. The reaction plane and centrality was determined using the BBC and the tracks from the drift chamber and the pad chambers. The plot on the right shows the PT spectra of identified particles for different centralities in gold-gold collisions in solid circles and D-gold collisions in open circles for positive and negative pions, kaons, and protons. To notice is the fact that the PT range for different particles is different, which is determined by the separation in TOF. Precise measurement of electrons and photons has been one of the most important charges for PHENIX. For this purpose, we use the ring imaging Cherenkov detectors and the electromagnetic calorimeters. Cherenkov radiations are emitted when a particle traverses medium faster than the speed of light in the medium. Cherenkov radiations in carbon dioxide radiators were focused using spherical mirrors on a surface of photomultiplier tubes to distinguish between electrons and hadron tracks. The Cherenkov threshold for electron is 20 MeV, while that for charged pions is 4.9 GeV, hence allowing for discrimination between electrons and hadrons to up to 5 GeV. Just a fun fact here, the shape of the mirror, which is shown on the figure in the left in the orange color, is actually the inspiration for the PHENIX logo. The top right figure here shows the dimensions of the RHIC, and the bottom panel shows the actual size. As RHIC is located behind the tracking detectors, the track projections of the spherical mirrors can be precisely determined. The ring size is basically given by the numbers of PMTs that were fired. On the right figure, the power of RHIC is shown. The plot comes from one of the earlier runs, and hence it is low on statistics. For different PT ranges from 0.3 to 1.2 GeV, the distribution of E over P is shown. We know for electrons, E over P should be around 1, where E is the energy and P is the momentum. The green line here shows the raw spectra. No structure can be seen at all. If at least one Cherenkov hit is required, what we end up getting is the black spectra. Blue is the estimated background, and red points are basically black minus blue, which is the electron signal. The distributions are relatively broad, below 1 GeV, as the resolution for E over P measurement for the energy resolution part is not very optimum. Electromagnetic calorimeters can be used to measure the total energy deposited by electromagnetically interacting particles, the electrons and the photons. With fine enough granularity, it can also measure the position of the hit and also the time of flight. While electrons and photons deposit all their energies in the EM-cal, the hadrons leave behind the minimum ionization energy. In order to better understand the systematic uncertainties, two different types of EM-cals are used in PHENIX. The lead scintillator, which is a sampling calorimeter. It consists of 6 sectors, 4 in the west arm and 2 in the east arm, and lead glass, which is a Cherenkov-based calorimeter, which is installed in 2 sectors of the east arm. The figure shows the discrimination between hadronic and electron clusters in lead scintillators in the top panel, and the lead glass for the bottom figure for different energies of the incident particle. A total of around 15,600 towers for lead scintillators and around 9,000 towers for lead glass are installed within the PHENIX acceptance. A cartoon of the towers for both the EMCALs are shown here. Both the detectors have excellent energy resolution, and the time of flight can be obtained from the formula that is given below. So shown on the left is the direct photon measurements for 0 to 20% gold-gold collisions at 200 GeV using 3 different methods and 3 different data sets. The red and the blue points are from external conversion method, when the photons are reconstructed from electron-positron pairs with the data taken in the year 2014 and 2010 respectively. The conversions were measured using the silicon vertex detector for the former and backplane for the hadron blind detector for the 2010 case. The black points were measured using the virtual photon technique. The green points were measured using real photons in the calorimeter. Also shown are the NCOL scaled PP fit and the PQCD curves in solid red and dashed blue lines respectively. The agreement between different data sets and methods is remarkable. On the right, we have the dielectron invariant mass spectrum with its various component identified, shown for PP collisions at 200 GeV. In the year 2012, silicon vertex detectors were installed as an upgrade to tag decays from heavy flavor hadrons in both the central and the forward arms. The detectors had full azimuthal coverage. With the position resolution of about 25 microns, these detectors enable the measurement of the distance of closest approach for secondary tracks to better than 200 microns. A notable measurement would be the semi-leptonic decays shown in the left figure for different centralities of gold-gold collisions at 200 GeV, for charm on the bottom, charm on the top and bottom in the lower panel. Nuclear modification factor for electrons from charm is shown in green and bottom in blue as a function of number of participants on the top right figure for different PT ranges. The bottom right plot is the state-of-the-art unfolding technique to separate charm and bottom enriched fractions based on the distance of closest approach measurements. The particle identification in the forward arms can be done using the forward vertex tracker and the muon detectors. Muons are one of the cleanest particles to detect as they require a lot of material for complete absorption. In order to reliably measure muons, 3 layers of trackers are in the magnetic field after the absorber. Thick layers of steel plates are used to measure its energy. Shown on the left is the nuclear modification factor of JSI from small to large collision systems as a function of number of participants in the nucleus going direction on the top panel and small system going direction in the bottom panel. On the left is the only Drellian measurement from RHIC for PP collisions at 200 GeV. To summarize, what started out as a very specialized detector to measure electrons and photons ended up being really multipurpose and provided complementarity to measurements from STAR. A good lesson to learn would be to have enough room for future upgrades when designing large-scale experiments, because over the years of its operation, a number of specialized measurements could only be possible due to the same. A notable mention, which I have not discussed in this presentation, would be the hadron blind detector in addition to the silicon vertex tracker. I leave you with the PHENIX t-shirt plot, the nuclear modification factor of a plethora of identified particles for the most central gold-gold collisions at 200 GeV, exploiting the capabilities of PHENIX. It is an example of 22 plus years well spent doing physics measurements. Thank you.
Thank you, Roli, for this nice talk. The session is now open for questions related to this presentation. So I think we already have a few questions in the chat box. So Subhash has asked, how do you get the start time for talk?
The T0 is obtained from the BBC. So if I can just go. Okay, so with T0 from the BBC and the time of arrival at the TOF, you can get the time of flight.
Right. Subhash, does that clarify?
Yeah. Thanks, Roli. Yeah. Okay.
Okay, thank you. So there is a question from Rishi that at LHCb, we had a talk last week. So the Cherenkov detectors can be used to distinguish PT greater than 2.5 GeV hadrons like pions, protons, and electrons. So the question is, can something like that be done here at PHENIX also?
As far as I know, it's not very efficient. The purity is not that good to distinguish particles just using Cherenkov radiations. And the reason is because like PHENIX uses these spherical mirrors. So if two tracks are parallel to one another, they would sort of form the same ring because of the geometry, and hence it would become very difficult to distinguish particles once everything start radiating Cherenkov radiations.
Rishi, you have some further question on that?
So it's because of the geometry of the detector is different from LHCb. You can't do the same technique here.
Yes.
Okay. Thanks.
Okay. So if there are there any more questions? Otherwise, we can also open up the session for the panel discussion. In that case, I would like to hand over to Subhasish for moderating the discussion session.
Thank you, Sandeep. Thanks, everybody. Hi, Roli.
Hello.
After a long time. Hi.
Yeah.
Okay. So I think it's a privilege that you guys have asked to kind of moderate this session. Now, what I could collect is that there are 4 presentations, including Roli's one. Roli is on PHENIX, then Chitrasen on STAR and LHCb, then CMS by YD and LHCb by Yanxi. So are you all present here first for discussion?
I am.
Yes, I am
You
present.
are here.
Chitrasen
Here,
is here,
Chitrasen.
yeah.
Yeah. So other 2, namely CMS and LHCb. I can't hear maybe. Okay. Anyway, so that's okay, no problem. Yeah. Okay. So CMS is here anyway. So that's good. So now, Sandeep, I do not know if you have any specific kind of brief to me, which you might want to go over, or you'd like me to kind of think the way I would like to have.
Yeah, I think you can proceed as you have.
So the way I understood this whole exercise is for our theoreticians like Sandeep, Rishi, and all others to understand the experimental result in heavy ions. And if there is something that they need to know a little bit better, and one of the items which initially, at least when I was asked, was said is a completely experimental, quote unquote, term, which is PID. But then they insisted, no, they have to know PID. So I'm sure they have not learned how PID is extracted, but at least they have an idea that all detectors do not give, or all experiments do not give the same PID performance for all particles. So the detector which, for example, Roli talked about is mainly for photons and electrons or neons, photons and electrons, but then STAR was for mainly charged particles. But that doesn't mean that they didn't measure the other ones as well, as far as practicable. Similarly for LHC experiments. Now only one experiment which appeared to me is not for heavy ion, at least dedicatedly, which is LHCb. So in fact, I wanted to know that if they have capability of taking data in heavy ion collisions, where the number of particles are very high, or they are limited to kind of measurements they do. So that is the first thing. So is there any comment from this?
I think this question to RCB is Yanxi. I don't have the camera. I think yes, actually, RCB has taken data since 2013. I mean, data about heavy ion collisions. We started with proton light with a few bunches. I mean, a few means much smaller compared to that being provided to ALICE, which is heavy ion experiment. Then we have some data of light in 2015. And then but also very tiny, just to test that we have we can reconstruct or collect this data. The biggest heavy ion data we had was proton light in 2016, about 30 inverse nanobar. It's already a lot, even though it's only I think a few percent, not a few, maybe 10% or something compared to CMS, ALAS, and ALICE. But it's a lot. We had many analyses with this data sample, proton light data, like charm production, proton light, the beauty production. And some also exotic, we know the X3072, which was also evidence in the data sample. And in 2018, we had a large light data sample, 200 inverse microbar, also a factor of something compared to ALICE, but it's a lot. But the problem for RCB is that we cannot reconstruct very central centrality, let's say very central light collisions. We can only do it up to from 100 to 60%, which is very tiny because it's only like 20 nuclear pair collisions compared to like a few thousand in very central region. If you look at the plot, it's at the very corner. This is due to the detector is saturated. The tracking system, that also the PID. So we basically all the pixels are heated, so you cannot find the tracking algorithm doesn't work anymore. So also that's why we have a very limited result for this light data sample. This is for run 2, which concluded in 2018. While for run 3, which was started early this year, we increased the granularity of the detector by a factor of 5. So that's also we can increase the centrality, not centrality, basically the number of nuclear collision from like 20 to something like 100. We can reconstruct data up to this like 30% centrality, but still very far away from the very central region.
So that means, yeah, we get it. So at this, you are far from real QGP one, which is the central one. But anyway, I think you have your own specialty. So in fact, CMS Atlas also, I think was not heavy ion detectors, but now they have sometimes much better results than dedicated ones. But anyway, so I think before I open up for questions from all the audience, I have only one question to all of you, maybe a very short one or two answers. Is that starting from Roli, the way I see on the screen, is that had it been today that you have to redesign PHENIX and you thought that yes, these would have been added as my more capability, then I would have been happy to have about in PID terms, of course.
Oh,
But
I would really want PHENIX to be azimuthally symmetric.
Okay. And that's true for all particles. But anything PID that you think, no, I would have had more of resonances or any other part PID capability that you think that could be augmented to the whole system?
So, okay, so the way RHIC was designed in PHENIX, because parallel tracks would produce the same ring, I would maybe want to change the structure of the mirrors so that we can increase statistics or like do a better PID for electron tracks which were parallel, but actually not coming from but were not ghost tracks, but actually like two different electron tracks. So that particular thing would be something I would like.
Okay, Chitrasen, you have any comment on STAR and ALICE that you can think of immediately?
Yeah, I think STAR was a very comprehensive detector. It has identification technique for hadrons as well as electrons, and recently also the MTD was introduced to identify the muons. Yeah. So yeah, that sector it was lacking. There was no muon detector. So, but later it was introduced. Otherwise, STAR has done a good job in particle identification. Even when the HFT was encoded, heavy flavor analysis was well done, and at low PT also. So I think it was covering all sectors. So, yeah.
Okay. And in Alice, you want to, because you seems to have talked about Alice detectors
yes.
also. Because Alice is kind of bigger form of STAR.
STAR. So what I did actually, I could not talk all the detectors of Alice because it was only 1 hour. So I mostly emphasize the common detectors, and mostly for time projection chamber and time of flight. I discussed those two major detectors which is used for particle identification. And then also I talked about photon multiplicity detector, but Alice has more particle identifier detectors, like even the ITS can be used. It is used also for the particle identification, as well as HMPID, like a high momentum particle identification is done using HMPID. And then the photons are also measured in the force detector, and muon also, muon trackage
forward region.
Yeah, forward region. So yes, Alice has more capability.
They have electron also in the middle application.
Yes, the electron also is measured in this one. That is the one which Cherenkov concept is used to identify. So yeah, so Alice has more capability and also more precision measurement than the STAR. And Alice is also evolving now. So with this RON 3, we'll have a new detector on ITS is upgraded and the TPC is upgraded. And again, there is plan for RON 4 and RON 5. So where there will be several new upgrades are coming. So Alice is much more well equipped for identification of particles as well as overall precision measurements. Yeah.
Okay. Okay. Good. Thank you. And it will culminate with Alice 3 at some point. So, yeah.
Yes. Now in Alice, this RON 3 actually will have more data rate also. It is increasing to 50 kilohertz. So also the reconstruction software is upgraded also. So that is another advantage in Alice now.
Okay. Now CMS so. Others, please prepare your questions for discussion, and meanwhile we just hear from CMS the same statement that what you think could have been improved so far as heavy ion collision data is concerned in CMS that you can think of.
Right. So I think if you look at CMS right now, right, is a very general purpose detector, very large coverage. The only thing that the current CMS detector does not have is the hadron PID. Right. So that is something I would like to have, and we will have that by run 4 using the timing. There will be a time of flight layer that will be added, which I presented in my talk, and those technology that will use a fast timing silicon technology, and that doesn't exist 20 years ago, right? So therefore, because CMS is very compact, you can't have large distance for path length for top PID. Therefore, if you want to get good top PID, you have to have very good time resolution. So these the emerging new technology make it possible to have finally we'll have the timing layer, and in addition, that's my dream would be that also the inner silicon layer will also have time replaced by the timing silicon at some point. The reason is that CMS has a very strong magnetic field, and the particle in the barrel region, particle below PT 0.7 GeV will not reach the timing layer that we are building now. So therefore, we'll have the full coverage of PIT to very low PT. That can be accomplished if one of the inner silicon layers is replaced by the timing silicon layer.
LGAD kind of thing?
Yeah, the current L gas probably is not going to be sufficient. We need a new type of L gas, like the so-called AC type of the L gas, and maybe by run 4, hopefully. But yeah, we'll see. But
Very
that's
good.
change I would like.
Okay, that's good. That's good. I'm sure. At least people always talk about they are very good at low PT, which is better than anybody else. So anyway, so now we open up. So I think I already see a hand. So it's Sorendu. It's your turn, please.
Yeah, thanks. Thanks for the nice presentations, all of you. One of the things that I noticed when I try to use ALICE and CMS data, correlate them, is the small overlap in PT, right? And a question to both of you, partly Wiley answered this question, telling us how they plan to go to lower PT, extend the PID to lower PT. But Chitrasen, what do you think you can accomplish in ALICE? A good PID, good purity at higher PT.
Yeah, I think it is continuation of your question which you had asked me. So ALICE, yeah, so ALICE has at low PT mostly 3 detectors which gives us PID, that is a ITS tracking system, and then time projection chamber and time of flight. But as you know, when they overlap all this spike AP at the minimum ionizing particles region, in that region, it is very difficult to identify the particles. But as you go again high PT, then there are new detectors like HMPID as well as a relativistic rise method is used to identify the particles. So that is why you asked whether a machine learning technique can be used to identify in this region where there is overlap between pi and kaon proton. So I saw already ALICE has some algorithm was developed for this particle identification using machine learning. So, but the performance was checked using different techniques. Actually, it was a random forest approach which was applied for the before run 2. So, but the only problem was to implement that in the ALICE framework was difficult. So that is why not many analysis was done, but it has improved the performance of PID at the intermediate PT region. But now with the software upgradation is happening for run 3, in addition to that, ALICE is also planning to use this machine learning technique using this domain adaptation neural network. So in that technique, so they are able to actually, they have demonstrated that we can improve the particle identification in those regions where there is a large overlap, like kaon proton separation can be better done using this machine learning technique. So I think ALICE is also software direction also trying to improve so that particle identification can be done in all PT region with more precision. Yeah. Okay. If it answers your question.
Yeah, so Surendu, is it okay for you, or you would like to?
Can I ask a follow-up question?
Yes, sure, go ahead.
Yeah, so I mean, I understand this direction, and we had the discussion during your talk.
Yes.
But right now, my question was more in the sense of, there are regions, as you're aware, where these different bands begin to merge. You can probably push the identification a little better by software, okay, by these methods. But would there be any hardware element that you would like to add in future to improve that? And that's a question that's actually not only for ALICE, but also for STAR, and similarly for Roli as well. I mean, PHENIX also has that same problem, right? So
yeah,
if both of you could take it one. Yeah.
At some PT, I believe that this DEDX kind of, or even time of flight, will merge. And
yeah, right. So if you can
only way is you have to improve the resolution of those bands. So
but if you can is it possible? So my question is it possible to add any other kind of detector which would remove that ambiguity?
Yeah. I am sure it can't remove completely because theoretically also those curves come pretty close. Now, if you have a detector where the band is higher, they will start overlapping more and more. but if you can make the band smaller and smaller, you will certainly improve upon it.
Yeah, so I understand that the bands will merge. So this kind of detection technique will always give this problem with PID at this in this region. So my question is whether it is possible to add other hardware which can remove the ambiguity that's present in this method.
Sure, I agree. So I would like to hear from, of course, both Roli and Chitrasen have been mentioned. So I will give Roli first chance to Chitrasen answer.
I think Roli also has something to say.
Yeah,
sure. I will hear from him because CMS is one of the most famous detectors for this. We'll hear from all four. So let's start with Roli and then we'll go ahead. Okay.
So Phoenix died in 2016, so there's nothing we can do about proving Phoenix. But but the thing is, so in order to uniquely identify a particle, you need to measure its two of the three things: energy, time of flight, and the momentum. Okay. With most of the measurements, if you have two of the things which are precisely measured, you uniquely identify the particle. In case of ambiguity, you can use the third method. But all of the detectors have technological constraints right now. So we can push as far as the technology goes. We can come up with new technology R&D in the meantime, and in future, we can hope to resolve these issues. But as of now, we can just try using all three techniques to get a better precision and a better accuracy.
Thank you, Roli. So, Wiley, do you have any comment to make? Maybe your improved silicon detector might help or some other detector.
Yeah. So just want to small comment. So the way you can push it is there are two ways you could push it, right? So you can make your detector for time of flight, for example, you can make the time resolution better and better, and that will push the separation further in momentum. For example, in the current the LGAS, we can the LGAS for EIC, electron ion collider, we're trying to build, and our target is 25 picosecond for a single hit. And there are also other type of technology like the LAPVD, which have shown at smaller scale that they can get 10 picosecond. But the current problem is they are very expensive. It's hard to build at large scale. Yeah, but so in principle, if you keep coming up with new technology to push the time resolution, then you go further. Or alternatively, you move your detector farther away. And right, so you increase the path length, then you also can push further. But it has to be reasonable, right? So any detector a few meters long you can't go beyond several meters long. So yeah, that together, I think the time of flight is, I guess, up to 10 GeV. You are not going to pass beyond 10 GeV with a reasonable assumption of technology you can get. Yeah, so I think beyond that, the only technology that I'm aware of that can pass beyond 10 GeV is the gas channel curve detector.
Okay, that's correct. Okay, Chitrasen, you want to make any comment or?
Yeah, hardware-wise, I think in Alice with this new ITS, which has all the 7 layers are pixel detectors. Earlier it was a 2 pixel layers and a 2 drift detector and a 2 strip detectors. But now all the 7 layers now for pixel detector. With that, I think the low PT DDX measurement will improve. So that may help in identifying the particles. And not at the intermediate PT very well, but at low PT it will be much better. Now we can go to the very low PT around, say heavy flavors can be measured up to 0 PT. That is the main idea for improving the ITs. Yeah.
Okay, Yanxi, you want to make any comment on this general problem?
Yeah, actually, think about the RCB, and also there are many people with the RCB to think about how we can improve in the future about, RCB basically limited by the tracking, but if you solve the problem for the tracking, then you have other problem, for other detectors to have a similar performance for the PID. But I don't know the answer. There are studies trying to, let's say, make sure, to use pixel detectors, silicon detectors for all the tracking system. But I don't know if it will solve the problem of tracking to separate all the tracks, since we are working RHCb working in the forward region for the same rapidity coverage, but the distance is much smaller compared to mid rapidity. So I don't know the answer. So but definitely
no, it's okay.
To increase granularity is a must, I think. And the other way for RHCb and for other LHC experiment for the future upgrade for the high Lumi, let's say, they were thinking use timing detectors. You don't separate it in the 3-dimensional space, but you can separate by adding the timing layer since different tracks arrive at different time. So this might help since you don't you separate the tracks in the 4th dimension of timing. So maybe this can help to make the traction software work. But this is just idea. There's no real application of such technology with a large dimension like for RHCb and other LHC experiments. For the RHIC detectors, I think this is even more challenging. I think because for now for the readout of the RHIC, because if you want to read the Cherenkov ring, you need to also have a pixel like photon detectors. I don't know how much we can improve to increase the granularity or reduce the size of the photon readout in the end. Because if you have many tracks, if you want to make sure the rings they don't overlap or to separate different rings, you also need to like for the tracking system. But this is in general. The other thing you want to improve, not only for the heavy ion but also for the heavy flavor core physics or RHCb, to cover the very low momentum and high momentum region. If you remember correctly, we have showed the slides. We have a very good separation of different hadrons at mid momentum, like a few tens of GeV. But it's not the case for the very low momentum range, a few GeV, and also not good for momentum above 1 GeV. It might not be so crucial for the moment, but if our physical program expands, you have many final state particles, the efficiency is not so good anymore. Since if you lose a few points here for many different many tracks, you lose a lot. So our estimation that if we can let's say expand the moment coverage for the RHIC up to 150 GeV, let's say, we can gain about let's say 30% of up to 50% efficiency on for the separation of different charge hadrons. That's a lot. And the technology, the ideas was to there's some preliminary study using the transition, I don't remember the name I mentioned in the slide, transition radiation detector, which covers high momentum range. While for the low momentum, there was idea use the torch using which is a TOF detector, but not measuring directly the timing of some let's say a scintillator. It used the Cherenkov photon radiated. We have a quartz where the charged particle will produce Cherenkov photons within the quartz, and we use Cherenkov photons to detect the arrival time of the charged particles instead of the ionization of this charged particle, because the Cherenkov photon is very prompt. So we can with this kind of technology we can detect low momentum. We can separate charge tracks of low momentum. Okay, this idea, not my idea, actually, the idea that we
circulated with I think, I think this gives a good direction. Of course, there is a follow-up question from Shorendu about Whaley's one, whether putting one near one far of the concept that he has said will help. Now, of course, Wiley has agreed that yes, it could help even putting more layers in between, which will essentially give different distance. So that's very good. So now there is a question from Rishi. So Rishi, go ahead.
Yeah. So Vedi, if you want to say something, you can go ahead first.
Yeah, I just want a quick follow-up on that question. Indeed, I think for me, the ultimate dream would be the entire silicon tracker every layer has a timing. So not only you measure the position and the timing, like a 4-dimensional, so-called 4-dimensional tracker. So you get momentum and velocity. So, and we are not quite there yet, but I think we're going in that direction.
Okay, very good. Thank you. Okay, Rishi.
Okay, thanks. So this is to Yanxi. So obviously LHCb has studied the exotics in PP quite a bit. So is there a program to look at exotics in lead or P-lead, and what's the plan related to that?
But they have limitations in centrality, right? They can go up to 30% centrality, more than that. Not more
Thanks
than
for
that.
thanks for the question. Yes, that's right. So to do it in lead it is I think difficult. There's I think I read some papers about exotic in situ lead degradation, where since you have I mean for heavy flavor you have multiple heavy charm parts produced, so there's higher chance to produce exotic hydron, let's say CC states. But that is at least for the moment is not realistic, maybe for future. Well, in general, for the exotic study RCB, indeed there are a lot of analysis in PP. But for P-lead, the limitation is for P-lead, I mean for lead, limitation is for the tracking, but for P-lead it is not a problem. So some intermediate step, let's say. But the limitation for RCB is a luminosity in the past. We were not provided with a very high luminosity, because for Alice and RCB they are competing with each other. So you want to have a lot more lumi for Alice, we have to sacrifice RCB. So we don't have many more lumi than what we need. So we don't have a clear signal of some exotic signal in the golden stem RCB deployment yet. But we do see evidence of X1372, which is the first exotic candidate. I don't know if you saw it in some conference where we do show this plot, some hint of signal, exotic signal input that data. Well, I think for heavy ion, usually we mean lead proton lead, but the very simple proton is also interesting, because over there we have many, I mean, very simple, I mean, a collision of a very high multiplicity for proton collision. Over there, we can also do some studies. We make analysis of exotic production as a function of the multiplicity, which also gives some information about the nature of these states, and some, I mean, maybe also some interaction, mechanism of the proton at very high multiplicity. So one short answer is yes, we have we have ideas within RCB about these kind of studies, but for the moment there are some limitations. But in the future, there are many people pushing for this direction. Okay.
Okay. Thank you. Thanks a lot. I think we are almost kind of close to our time at 7:30. But I would like to hear if there is some pressing questions, because in fact, personally, I wanted to open up the discussion on machine learning, because everybody is nowadays using machine learning to do everything and thinking that that is the magic potion and will solve all the problems. They're in hardware, which is not true. So we wanted to have a view of all the 4 experiments that, so far as PID is concerned, how they are using machine learning. But I'm not sure if there is time for that today. So I would better rather hear if there is more questions from colleagues here.
I have a question, Subhasish. Yeah, so this is about this PID for lambda. So lambda, what we hear is that because there is a weak decay, so it seems like event by event one cannot do that. At least STAR cannot do, but I think we have results from LHC, Alice possibly, and they somehow managed to do, it seems, event by event lambda. And then later on, I think there were developments from STAR that they could even do lambda event by some DCA cut or something. But I haven't heard what were the further developments? Because in the beam energy scan, I usually don't see the lambda flux event by event being done at lower energies, for example, or
No, what do you mean by event? You mean that every lambda you have to count, or you count the number of lambdas in an event on an average? Or
yeah,
in a,
I mean, not on an
which one
average, but in
purity?
every event you count how many lambdas to do, for example, net lambda movements.
Okay, I understand it. Okay, so Chitrasen, you want to comment anything on that?
Yeah, I have also not seen the measurement on event by event measurement, but I think we can do it because event by
Yeah,
event,
I also think
we can reconstruct the secondary vortex, and the way we are doing the analysis also now, like putting this topological chords we are reconstructing. And also recently there are new techniques which are used for this lambda reconstruction. So but I have not seen the result, but I think it is possible for STAR and ALICE to do it.
Okay.
Yeah, I also feel so. ALICE, I think, is they have more number of particles.
Yes.
So they are, even though they measure number of lambdas in an event, I think they can even get a number, which is statistical measurement within an event, and then get for every event. Maybe something like that.
Usually I've seen that when they quote, for example, yield of proton, they say that it is not the weak decay contribution from lambda is not included in that. So they have ways to correct for that. But
no, but that's a different. I think the way you ask the question is event by event measurement of lambda. That means you have to measure lambda yield in every event,
right,
and then make a distribution and look at the width or whatever cortices or whatever you want to look at. But when you talk about inclusive measurements, of course, there are some number of lambdas counted, divide the number of events, and then correct for the feed down. That is well established method. But event by event, the number that you extract, whether it's reliable or not, that I think was the question to start with. And that's okay. Nasim might have something to add to because he has raised his hand. Nasim, please go ahead.
Yeah, so I just want to say that and STAR already measured this event by event lambda and published the net lambda fluctuation measurement recently. So it is possible because pure efficiency will be very low because you have to put very strict event topology cut, but it is possible. BS Energy STAR has published a net lambda fluctuation paper.
What is the purity like?
I do not remember right now. So maybe Subhas
has already sent the link so one can have a look.
Yeah,
I think that's good. That's a good point of discussion. So Sandeep, I think should we close today? Because if you ask me, you can continue for long, but then what's your boundary conditions? I don't know.
Yeah, I mean, so we could ask if there are more questions or other.
Yeah, if there are more questions, please go ahead.
Can I just comment one thing for Sandeep?
Sure.
Yeah, Sandeep, so this proton measurement earlier STAR was not doing this feed down correction, but recently the new publications, if you see, STAR started doing the feed down correction for the proton from the lambda and a higher resonances also. Yeah, that is the one thing.
So how do they manage to do that?
Because now we have measured a lambda spectra, so we can use the data now. Data-driven method we can follow. Yeah.
Okay. Thanks.
So then I have another comment to Rishi's question, which was asked in the last session. So Rishi had asked me regarding that why the STAR error on the helium-3 and anti-helium-3 mass difference was lower compared to ALICE. So the main reason it was actually the method which we followed. Actually, it was not directly measured the helium-3. It was using the two-body decay from hypertriton and a three-body decay for hypertriton. In a two-body decay, you have helium-3 plus pion. In a three-body decay, you have a deuteron plus proton plus pion. Then if you just take the difference, mass difference between these two methods, that will give you mass difference in
Hello, maybe I don't know if my end problem or your end.
I think Chitrasen's end problem.
Okay. So sometimes it happens, you know, that. Yeah. Okay. So Chitrasen is frozen. Looks to me.
Yeah.
Yeah. So any comments?
Okay.
I think he has come back.
There is some Tribhuvan Parida, please go through your question.
Sorry, I think I got disconnected in
Yeah,
between.
you got your last sentence of taking the mass difference, and then you got choked.
Shall I continue?
Yeah, maybe you can complete it certainly, because everybody
Yeah.
wants to.
So yeah, this paper, actually this is explained in the Nature paper from STAR. Just that the mass difference between these two techniques, like a two-body decay and a three-body decay, if you take the mass difference, it will come out in terms of a mass difference of helium-3 and deuterium. So helium-3 is constant from the hypotriton measurement. So that is how it is lower compared to Alice measurement. This is
Okay.
just a, yeah, some
Yeah. Thanks a lot.
Thank you.
Yeah.
Okay, Tribhuvan, maybe yours is the last question for today.
Yes, sir. So I have seen earlier Alice measurements of charge particle yield. The pseudo rapidity coverage is from -5 to +5. So still now is the wrong when the Alice run is going. Still the coverage is charge particle coverage is -5 to +5, or they have increased it, or any changes in that?
Yeah, Chitrasen, do you want to comment? Has
Yes.
Alice increased or decreased their pseudo rapidity coverage?
No, actually this measurement usually we do in mid rapidity. It is not that Alice does not have coverage.
No, but he is talking about the pseudo rapidity spectra, which is from -5 to +5. So charge particle spectra. So that might have been done for DND eta only. So that gives that much coverage.
Measurements are also there from -5 to +5, only for charge particle. Maybe
only for charge particle.
Yes, so this measurement which you are talking about, it is just the mid rapidity measurement, right?
No, sir. I am talking about charge particle. So for identifying.
No. So far as Tribhuvan, so far my understanding is concerned, of course, Chitrasen might correct me. I don't think there is any change in the pseudo rapidity so far as Alice detector is concerned at this point of time.
Yes, but Alice
total magnet is same, length is same, theta is same. Now when they go to Alice 3, which is in the level of discussion now, I think they will increase the eta coverage huge, in the sense if it is ±5, they might go to ±8 or something like that, which is basically to get the delta eta correlation and all other things, right? So far as present is concerned,
sorry, please go ahead.
Go ahead, Chitrasen. Go ahead, Chitrasen.
No, I was just asking, the question was 0.5 or 5?
5.
Okay. I think then there is no. I thought it is 0.5. You are asking.
Okay.
No, how much pseudo rapidity the particle is? One can identify at Alice.
No, the charge hadron, up to 0.5, because that is mostly this FMD, which gives the charge particle in forward rapidity. I don't see any other detector which is currently upgraded to give higher rapidity coverage.
No.
His question is that what is the PID capability? Up to what in rapidity?
In the rapidity, I think PID
a little bit less, I guess.
Little bit less. I think 1 point something rapidity coverage.
DDS becomes very bad. Number of points will be very less. So I don't think that.
Yeah,
I don't have the number.
I don't have the number also. Yeah, it should be less than this charge particle.
Yeah. And the electron positron from up to which rapidity?
That is mid rapidity mostly, because that is from the mid rapidity detector.
Yeah, mostly it is the mid rapidity detector, which is like ±1, 1.2, like that region. But yeah, I think PID is mostly done in mid rapidity, but forward rapidity only the muon measurements are done. Muon and photon measurements are also done.
Correct.
So another.
Okay, so yeah, you want to ask one more? Yes, go ahead.
So in STAR experiment, that EPD which is installed in larger rapidity,
EPD you are talking about? What exposition detector?
Yeah. Yes, that is event plane detector. EPD he is talking about, I think.
So it can only identify the charge hadrons.
Yes. Yeah,
Yes,
EPD is only for charge hadrons. Yes.
This essentially measures the
Right.
number of charged particles in different azimuth and gives you the reaction plane.
Yes.
Okay, so Rishi has some comments here. Can I get a quick question in before ending? Yes, Rishi, you're welcome.
Just one. I think this is a continuation of the discussion between Vedi and Surendu. So one of the low PT particles that we thought about were J size at low PT, and once again at CMS it's very difficult to get the low PT J size. So my question was, with the upgrade. Is there some idea of how low a PT of JSI can one get to at CMS?
Yeah, Wiley, any comment?
Yeah, so let me just pull up the slide I showed last time. So the low PT for the J-side decay to dimuons is very hard for us to do because of the strong magnetic field. So one possibility that we discussed a bit, in principle, CMS can lower the magnetic field to 2 Tesla. We have the map there, but usually that's not something we do unless there's a strong physics argument to do that. But that's one possibility. If we lower the magnetic field to 2 Tesla, we can do J-psi down to 0 PT through the dimuon decays. No, without that, the other possibility is by the time we have the MTD detector, the time of flight detector, we can measure J-psi through the hadronic decays. So it will decay into a proton antiproton. The Bronson ratio is much smaller, but it can cover a phase space that we cannot cover using the dimuons.
Okay. Yeah, that's
okay.
Correct. Yeah, that's very interesting. That will be very interesting. I have not seen anybody doing it. So.
Okay, thanks.
Okay, thanks a lot. I think now it's time because there is no end to it. So Shorinda has written to everybody. Thank you to all speakers for their talks and for participating in today's discussion. And of course, he has thanked me. So big thank to you also. So thanks everybody. I am sure now this is the beginning of the series, which essentially our theoretician friends are trying to learn how pure the data that we give them, or we put only systematic error with big band. So I think you already have some idea about it, and I'm sure the next real physics discussions will be more enriching. So thanks a lot, Sandeep. Now over to you.
Yeah, thank you, Subhasish.
Thank you. Bye-bye.
And thank you to all the panel members, Roli, Chitrasen, Yanxi.
Thank you so much for the opportunity.
And thank you to all the participants as well. And with this, we close the discussion on the PID. And from next session, we start our discussions on the global measurements. And then we have other topics as well coming up. So please join us in future as well. Thank you. Bye-bye.
Thank you. Bye.
Bye.